Although we don't often think about it, we live on a planet. What would it look like to an alien studying our planet for signs of habitability or even life? Understanding our own planet is a key to understanding other planets. Join me as we study Earth with the purpose of using that knowledge to understand the conditions of other planets. In the process, we will hopefully learn a few things about our own home, where we've been, and perhaps where we may be going. Stay tuned. Under our feet, the Earth consists of several layers. We stand on the crust. Underneath this relatively thin crust is a deep layer of rocky material called the mantle. The mantle surrounds a liquid or molten outer core. A solid inner core is at the center of our planet. How do we know this? Earthquakes. We know earthquakes create different kinds of waves, P waves and S waves, each traveling through different types of material. The type of wave we measure from a distant source gives us clues to the material in between. These waves provide an abundance of measurements because we have lots of opportunities. Here is a map showing the location of common earthquake sites. Notice that they are not random. They form very clear and recognizable shapes. They form the boundaries of what we call tectonic plates. The measurements have resulted not only in a picture of the layers, but also the densities of each layer. Notice how the densities get higher with increasing depth. It is extremely unlikely that the Earth formed this way. Rather, this differentiation, as we call it, is telling us that the Earth had a molten or liquid phase, allowing heavy elements to sink to the gravitational bottom. Earthquakes happen as the tectonic plates move and collide. Notice that some plates move in a north-south direction. Others move east-west. The movements are very slow, about the same rate as fingernails grow. But it's enough that we feel the collisions as earthquakes. When plates collide, mountains form. Or plates can move apart, like in this image. New mantle must fill in the gaps. But what would make a tectonic plate move? In a word, heat. Heat produced internally creates moving currents. Like boiling water, the hotter material at the bottom rises to the surface. Anything on the surface will be affected. In the Earth, the currents of rising and sinking material create a force that moves the crust. The heat comes from planetary formation via the process of accretion. Gravity compresses the material and in the process heating it up, as well as the constant impact of the accreting bodies. All of these produce heat. In fact, about half of Earth's internal heat comes from the process of formation. Radioactive decay is another source of internal heat. Post-formation impact events also create internal heat. Impacts were much more common in the early solar system. Another consequence of heat is volcanoes. Volcanoes form either along tectonic boundaries or on top of local mantle hotspots. Two types of volcanoes are found on Earth: shield volcanoes and composite volcanoes. Shield volcanoes are those type found often in Hawaii. An example of a composite volcano can be found in Washington State's Mount Rainier. Volcanoes are the result of hot magma breaking, sometimes violently, through thin spots in the crust. The difference between the two types is significant. Shield volcanoes are characterized by slow, thick magma flows that create shallow slopes that shape under the influence of gravity. The height will build gradually as new eruptions flow over previous eruptions that have solidified and cooled. In contrast, composite volcanoes have tall, steep sides and often erupt suddenly and violently. Ash can rise tens of thousands of feet high and be spread hundreds of miles. The ancient city of Pompeii was buried by the composite volcano, Mount Vesuvius. Composite volcanoes require plate tectonics, and they also require the presence of water. Vapor pressure from superheated water helps to increase the force of eruptions. Because of these requirements, composite volcanoes are unique to Earth. Shield volcanoes, on the other hand, are common throughout our solar system. Main difference between the two types of volcanoes. Further evidence of Earth's internal structure is the presence of a planetary magnetic field. We know of it because we can navigate using a simple compass. For a terrestrial planet to have a magnetic field, it requires three things: a solid inner core, a liquid outer core, and rapid rotation. A planetary magnetic field is similar in concept to a simple magnetic motor. If you remove any of the three parts, the magnetic field will no longer be present. Visual evidence of magnetic fields are auroras. Visible mostly in the northern or southern polar latitudes, they occur when charged particles from the sun get trapped in Earth's magnetic field. Auroras can be quite spectacular. They're also easily visible from space. We can observe these events from quite a distance, occurring even on other planets. Earth's magnetic field is vital to the habitability of our planet. The magnetic field deflects cosmic rays and solar wind. Charged particles would otherwise strip away the ozone layer that protects the Earth from harmful ultraviolet radiation. Additionally, cosmic rays are damaging to the DNA in living tissue and can result in high rates of cancer. We cannot survive without our magnetic field, or some equivalent protection that protects us from the space environment. The Earth's atmosphere is all that protects us from the harshness of space. That's the thin layer of hazy blue in this photo taken from space. The current atmosphere is actually thought to be Earth's third. The first consisted mostly of hydrogen and helium. The second, mostly carbon dioxide. And the third, our current atmosphere, consists mostly of oxygen and nitrogen. What makes us believe that we had three atmospheres? Our current solar system formation models indicate that Earth, and everything else in our solar system, formed from a solar nebula, consisting of mostly hydrogen and helium, the two most abundant elements in the universe. These elements and their quantities are shown here. So why do we believe that this was our first atmosphere? First off, the Sun has a composition similar to this cosmic abundance, as we call it: 74% hydrogen, 25% helium, and traces of other elements. By cosmic abundance, this simply means that the same elements in the same quantities occur just about everywhere else in the universe. And we see the same composition on Jupiter as well. But don't forget about the other gas giants, because they're all similar. So the solar nebula had these elements in these quantities, and every planet started out with these same basic ingredients. But on Earth, hydrogen and helium did not last. Why would this be? Well, remember thermal escape. Hydrogen and helium are very light. With Earth's proximity to the Sun, hydrogen and helium were heated so that they escaped the Earth's relatively weak gravity. Fortunately, we had a replacement. Earth's second atmosphere was generated by volcanism and plate tectonics that recycle material from Earth's mantle. Remember also that volcanoes spew gases trapped in the mantle in a process called outgassing. Outgassing consists mostly of greenhouse gases, like CO2, water vapor, and others. Outgassing by volcanoes is still going on today and releasing the same elements. As the greenhouse gases were warming the planet and liquid water was forming, the CO2 dissolved into rocks and oceans. Your favorite carbonated water is an example that CO2 readily dissolves inside water. And more importantly, plant life began to convert the CO2 to O2. These processes converted our outgassed atmosphere to today's atmosphere that consists mostly of nitrogen and oxygen. And don't forget, not only does our atmosphere give us breathable oxygen, it also helps to absorb harmful radiation and cosmic rays from space. Another important consideration involves the distribution of heat. Since most planets have small obliquities, the equators get the majority of the sunlight. However, global circulation distributes heat from the equator to the poles. Remember, hot air rises and cold air sinks. This means that the air from the poles would naturally spread out and move towards the equator. Each hemisphere would have its own circulation cell. Throw in some rotation, though, and those cells would break into smaller cells. Notice the rising and sinking air patterns. Rising air is associated with clouds and rain. Sinking air is associated with a very stable weather pattern that does not promote clouds and rain. This is why the majority of the deserts on Earth are at latitudes of 30 degrees and 90 degrees. Yes, the poles are considered deserts. Venus is an example of a global single-cell model. Venus's rotation is very slow and results in the single-cell pattern, with circulation from the pole to the equator. Note that the chevron shape, shown here, is due to the rotation effect called the Coriolis force, the same force that creates the familiar hurricane pattern on Earth. If you rotate the planet even faster, the cells split into even more zones. Jupiter is a great example. Jupiter rotates in only 9.5 hours, so its atmosphere consists of multiple cells per hemisphere. Our weather, like tectonics, is driven by heat. The sun heats the ground, the air near the ground gets hot, and it rises. Recall our boiling water simulation. Just like boiling water, when hot air rises, it cools and forms clouds. Clouds grow to the point where rising air from the ground cannot keep the water droplets in the atmosphere aloft, and they fall as rain. The presence of clouds cuts off the ground heat source, so eventually the energy driving the rain runs out. The clouds dissipate, and the cycle starts again. On Earth, rain and snowmelt cause erosion, removing evidence of past activity. The Moon is atmosphere-free, so its surface is a record of billions of years of surface changes. If it were not for the Earth's second atmosphere and the ongoing greenhouse gases, Earth would be a very different planet. Without the greenhouse effect, Earth's average temperature would be 31 degrees Celsius lower than it is today. The Earth's average surface temperature would be a very cold 17 degrees below 0 Celsius. That's about 1.5 degrees Fahrenheit. The climate on Earth would be very different. We would go from this very chilly climate to the more relatively comfortable and life-friendly average that we observe today of 59 degrees Fahrenheit. We actually owe our lives to the greenhouse effect. Greenhouse gases, like CO2, methane, and water vapor, and many other less common elements, allow light to pass through the atmosphere and heat up the Earth. The Earth re-radiates that heat back into space in the infrared part of the spectrum. Greenhouse gases, though, trap infrared heat, not allowing them to escape. They act like a blanket that keeps us warm. As with anything, too much of a good thing is never good. Just look at our neighbor, Venus. It is a great example of what can happen when we add too much greenhouse effect to our planet. We need to keep things into perspective, though. The primary contributor to Earth's temperature is the sun. However, we need to keep in mind that local conditions can and will contribute significantly to our temperatures, and this will be an important consideration as we look at the habitability of other planets, either in our own solar system or in others.
Reading unidentified vessel just entering visual.
But it's before a hopeless battle if tradition serves the gerbil well.
What is wrong? Whoa! What's wrong with you?
I know what you're planning, sir. I will not be surprised.
What are you talking about? Tracy!
Reading unidentified vessel entering just. Sir.
Data on acid. Then we've detected some sort of loose.
What do you see when you look out there? Home?